Okay, so today we're going to be talking about lessons 6.2 and 6.3, and we're going to be talking about triangle congruence. On the first lesson, we talked about showing that two triangles are congruent if all their corresponding parts match each other. And that's a really good starting point, because if you have an identical twin to you, all your corresponding parts and angles should be exactly the same, or you're not going to look like identical twins. So, for example, if the slant of your nose, that angling is different than your twins, well, then you're not going to look identical. And so, in similarity, if we've got two triangles and if they're going to be exactly congruent, mine are not, obviously, this has to match this. This has to be congruent to this. The bottom should be congruent to the other bottom. And then each angle should be matching the corresponding angle in the second triangle as well. And if you show that all three sides and all three angles match, well, then the triangles have to be congruent to each other. And we can show that all the corresponding sides match each other and all three corresponding sides match each other. If you just say all three sides are congruent, you're talking about an equilateral triangle. So you've got to use your words with precision as best as you can to be able to say, hey, are we talking about two congruent triangles or equilateral triangles? And so that's important. But the deal is this, with a triangle, you have something special going on because there's only three sides and three angles. Because we've spoken about the measure of an angle directly impacts the length of the side across it, like a big hug. The smaller the angle, the smaller sides across it in a triangle. In shapes that have more sides on them, it is not actually true. But in a triangle, the measure of an angle directly impacts the length of the side across from it. So if you have two triangles, and you show three important features match each other in those two triangles, then you actually have enough to say, actually, the rest will match as well, okay, because of that angle side relationship. And so we've got some shortcuts where you can show three strategic things match, um, and then you will know that the triangles have to be congruent, okay? And so this will prove that the two triangles are congruent. So this is kind of the theme of this chapter is, are the two triangles congruent and can you show it? Okay, without having to do all six. So definition of congruent triangles for sure is a method. Okay, when I ask you for what methods can you use? One of them is by definition of congruent triangles, which is all three sides correspondingly are congruent and all three angles correspondingly are congruent to each other. That is absolutely true, but there are several shortcuts for this. Well, first of all, triangle rigidity is a feature we need to know about. Triangles are rigid. Okay, once you have all three sides, well, then they're not going to change and bend and make different shapes. You're like, I had no idea that anyone would think about that, but they're not smushy. So if you got a triangle that's 3 and 4 and 5, and if you have another one that's also 3, 4, and 5, okay, those two will be congruent to each other. Okay, because whether you rotate them or reflect them, remember we did the isometric transformations, which were rotations, reflections, and translations. So you can have, as long as they have three sides the same, whether you rotate, reflect, or translate them, they'll stay congruent to each other. So that is a good thing to hold on to. You're like never worried about it, but that's that's good. Um, but one of the shortcuts we can talk about would be side, side, side. If all three sides of one triangle, okay, are congruent to the corresponding sides of another triangle, well, then guess what? Those two triangles will be congruent to each other. So if you notice this side matches this side right here matches this side here, and the bottom side matches this one right here, those will be congruent to each other. If the sides are congruent, the angles actually will be congruent as well. And you can tell if you put them on top of each other, they would match up perfectly. And so we don't have to know that the measure of each angle, but if all three sides are congruent to the corresponding sides of the other, that's enough to show that these two triangles will be congruent. And then the next thing would be if you know two sides and you happen to know the angle in between them. Okay, they call it the included side. Okay, you're like, what? If you saw me in person right a second, you would see me put my arms up like I'm between two people, putting my arms around them. Okay, and so just, like over the shoulder, like a picture. Okay, so if you're going to take a picture with your two best friends, one on each side, you're the included, like an Oreo, you're in the middle. And so, if you know two sides and the angle in between them, then and that is those three things are congruent to another triangle, then both triangles have to be congruent. The answer is why. Okay, the question is why, not the answer. The question is why. It has to do with um right down here. Because of the angle side relationship, we know that the angle size of a triangle is related to the length of the side across from it. Therefore, these shortcuts are based upon that. Okay. So consider this. What if I had this side here and I had this side here, but the angle was different? Okay. Well, then that would make this side longer. Okay. And so however, because the length of the measure of the angle impacts directly the side across from it. And so if these two angles are the same, they ensure that the side across them also is congruent to each other. And so um, that angle being the same and it being in between makes you know that all three of the sides will end up being the same as each other. Now, we can use we can write side angle side congruence. We don't have to use the word postulate, but notice these are postulates. They're true without proof. Okay. So these two right here are postulates. So they're true without proof. But if you write side angle side congruence, I will accept that. Okay. You don't have to remember which ones are postulates or theorems, but those two are postulates, true without proof. Okay. And same with this one too. Okay. This one's a theorem. Okay. I will not make you hold on to which ones are theorems versus postulates. But if you want to hold on to that, you're welcome to. Um, the next one is going to be, it just talks about what's an included angle. It's the one that's in between them. So A is included in between BA and BC or AC. So if you look at BA and BC, which angle is included? Well, which one is at that vertex in between those two sides? This right here is going to be the included angle. Okay. In between those. So if you've got side and then you got an angle and then you got a side. Okay. Um, let's just say this right here. We've got the next thing is going to be, I don't think I want to use pink today. Let's use blue. Okay. Angle, side, angle. If you know two angles and the included side in between them, so angle, side, angle. Well, because the angles ensure the sides across them from them have to be the same size. The side also helps. You will, in fact, have two congruent triangles if you know two angles and the side in between them. Okay, the included side in between them. So angle, side, angle is a shortcut proof as well. Again, the angles help control the measure of the side across from them. And this side right here controls the measure of the angle across from it. So truthfully, as long as you know those three things, two angles and the side in between them match the corresponding angles and side of another triangle, those two triangles have to be the same size. And then we also have angle side. So if you know two angles, and then the side after it. Some kids get real confused on this. Like, how are you doing different letters? What's the deal? Notice I know two angles, and the side you know is not in between them. And so you start with something you know. Okay, I know two angles, and then if I keep going around the triangle, I know an angle, and then I know a side after that. Okay. You can go either way around the triangle. You start with something you know, I know two angles, and then I know a side after it. Okay, if you tried to go the other way, you'd be like, let's try to go this way. I know I don't know anything that way. And so it's two angles and then a side following it. So angle, side would also be a proof. So that's a theorem, so one could prove it using there are postulates above it. We're not going to prove this necessarily. Okay. And then the last one would be a hypotenuse leg. A hypotenuse leg talks about if you have a right triangle. So remember, if they use the word hypotenuse, that assumes a right triangle. Okay, so if you know you have a right triangle, and then the hypotenuse of that triangle and a leg, one of the two, are congruent to another one, then you will have congruent triangles. So Notice they didn't spell a bad word here. So angle, side, side. No, they don't spell that. We don't use that. We say, hey, if you have a right triangle, then, and you know the hypotenuse and the leg of that right triangle, then you would say those two have to be congruent. So if you start with a right triangle and the hypotenuse and legs match up two triangles, then you will have congruent triangles. And if you think about it, you could do the Pythagorean theorem. And if you did the Pythagorean theorem on this one, okay, you would find this side would be 4. And if you knew that this was 5 and this was 3 as well, again, you could do the Pythagorean theorem and you would know this would be 4. So the right triangleness assumes that you would have side, side, side. So if the hypotenuse and leg match, all three sides would match of that triangle as well. Okay, so why is angle, angle, angle missing? Okay, that is not a valid proof. If you show it, if you think about it, angle, angle, angle. So if you've got like this right here, okay. What if you had a bigger triangle? Okay, if the angles match, that's going to be similar or proportional. Okay, similar. Um, and so it'd be like a dilation, okay, to dial it bigger or smaller. And we'll deal with that later this year, dilations where the proportions are the same, the angles are the same. So it'd be like so if you got real famous and they're like, let's make a Barbie doll about you. All your angles should match yourself. Okay, the slope of your nose, the slope of your shoulders, the proportions should match if they make a Barbie about you. All your angles would be congruent, but your lengths would be different. Okay, and so if you don't know any lengths, you just know the angles match, well, then they will be similar, not congruent. And the similarity in triangles and shapes is a much more precise situation than it is in life. If we're like, oh, they look so similar, they have the same color shirt on. No, that's not what we're talking about in math class. We're talking about are they similar proportionally, meaning their angles are the same, but their size is different. Okay. And so, anyway, it'd be like if you get real famous as well, and they're like, "Ooh, let's make part of the Macy's Day Parade let's make like a huge, 50 times bigger person of you to be like, let's show your face around the world." So again, angles are the same, but the size is definitely not the same. So those would be similar. And so the next thing we're going to talk about is I'm going to show you two triangles and say, would they be congruent based upon the facts you know about them? And so I will give you facts, but there are two things you can assume from any situation here. Yes, we can assume linear pairs. I don't know that we're going to use linear pairs very much on this situation. So I'm like, yes, you can assume that. You can also assume vertical angles. Okay, if you've got vertical angles, those angles will be congruent. And then the other thing you can assume would be um, reflexive sides. Okay, what's that mean? Remember, reflexive means a segment is congruent to itself. Okay, AD is congruent to AD. There are times, like in this first one here, where this segment here, notice it's part of both of those triangles. And even though that segment is part of both of those triangles, it doesn't change length when it looks at one triangle as part of one triangle versus the other. Okay, so although it's the same segment, it's technically part of both triangles and it doesn't change its length based upon that. So this will be congruent to itself. Okay, so in this first shape, we know that the bottom, okay, those two sides are congruent to each other. We know, secondly, that this angle here is congruent to this angle because all 90-degree angles are congruent to each other. And then thirdly, we know that this vertical segment here, although it's the same segment, it also is a member of both triangles. It has the same length, even if it's part of two different triangles. And so what we know that matches between those two triangles would be a side, okay, two sides match, an angle in between them matches, and then another side. So these two triangles could be congruent. Why? Because of side, angle, side. Okay, and we could say side, angle, side congruency. And you could write down if it's a theorem or postulate. I'm not going to make you hold on to that. Okay, so it's congruent by side, angle, side. two sides and the included or the angle between them are congruent in both triangles. This one, if you notice what's marked, okay, it's marked that this angle matches this angle, they're congruent. It's also marked that this side right here is congruent to this side right here. So we've got an angle and we've got a side that match in both. And then thirdly, there is a reflexive side as well. This side right here in the middle is part of both triangles and it retains the same length, even though it's part of both triangles. And now this right here is going to be, now you could look at it, so it spells angle side side. Proper people don't write that on their paper, okay? It's going to be side, side, angle. Yes, it is side, angle, side, side. And that does not prove it, okay? Because, not because it's a bad word, it's because you can have two different triangles with the same measure, okay? But drawn differently. Okay, so there are two ways to show angle, to do an angle side side sometimes. Um, and that doesn't prove that they're going to be congruent to each other. So if you look at this, this is angle side side and it's wider, and this is angle side side and it's more narrow. And so angle side side or side side angle doesn't work. Proper people don't write that on their paper, but so therefore not congruent. Okay, so if you have an angle and then two sides following it, okay, the angle is not included in between the two sides, then it is going to be not congruent. Okay, that's not they're probably congruent, but it doesn't have to be. Okay, and so we're trying to say, does it have to be congruent based on what you know? And so not congruent for that one there. This one right here, notice we know this side matches this one here, this one right here. They match each other and there's nothing else. Well, yes, there is. We can always see vertical angles. So this angle here matches this angle right there. So we've got side and the angle in between them. So that spells side angle side. There's two sides and the included angle in between them has to be congruent. So therefore those must be congruent to each other. And then the last one, we've got a side. Those two sides match. These two sides match. And the last thing we know is that this side in the middle will also be congruent because it's a reflexive side. So there, I should put three stripes on it. And so we say they are congruent because all three sides, corresponding sides, are congruent to each other. Okay, so we're trying to say, do we have enough information from the diagram just to verify that they must be congruent? Okay, and the thing is, you're like, but they all look like they're congruent. And the answer is yes. You cannot trust necessarily a diagram's like proportions, but we're trying to say in general, even if it's not drawn to scale, based on the markings, say if I tell you they're congruent, they are. Is that enough information, even if these are not drawn to scale, that these two triangles have to be congruent to each other? Okay, so be careful to use your logic, use those proof shortcuts to say, what do I know from the diagram, from the congruency documents, as well as these two pieces? Do I know enough to show, hey, even if this is not drawn to scale, they have to be congruent based on the markings I know. Okay, and so it's a little weird. We'll talk about this bit by bit this chapter. Now we're going to make some proofs. And notice this doesn't have any steps given yet. Okay, so we're going to practice writing our own proofs today. Okay, which is a good thing. Given the AC is parallel to BD. Okay, so we're going to mark it with two arrows. And also we are given that segment AC is congruent to BD. Mark it on your diagram so you can see it. So we're going to start the proof by saying that AC is parallel to BD, and that's given. Okay. And then we're going to also say that AC is congruent to BD. Okay, that's also given. Okay, so we've got a corresponding set of sides that are congruent. So we got S. You can write that to the side if you want to help you remember, but we've got a side. And then that's all we got. We're like, oh, great, awesome. But anytime you have parallel lines, you have alternate interior angles that are congruent. Okay, so um, there are a couple transversals. There's actually three different transversals drawn there. Is there an alternate interior angle that could be helpful to show that these two triangles, the two main triangles, are congruent? And the answer is this angle here will be congruent to that one there. And you see how they're alternate interior? And so we're going to call them out to say, hey, angle ACB and angle CBD are alternate interior. Why? Definition of alternate interior. And then because, remember this has to be, if they're parallel and they're alternate interior, what has to be true? Well, then they have to be congruent. So angle ACB has to be congruent to angle CBD. And why? Alternate interior angle theorem. Okay, so those three go together. If the lines are parallel and you have alternate interior angles, they have to be congruent to each other. So this one has to be congruent to that. So we technically now have a side and then we have an angle. Is there anything else we can do? Because we're out of givens, aren't we? Okay. Do you see that there's a reflexive side? Okay, so if we look at our diagram, the top triangle, so we've got, I'll get a brighter color so you can see it cuter. All right, so we have got a side here, the top, and then we got an angle here, and then we got a side. So side angle side is going to be what we use to prove that these two triangles match each other. So side angle side on the top one matches side angle side on the bottom one. And so we're going to state that segment, cover that up so crazily. That's going to be CB. Okay, so that's that green segment. So segment CB is congruent to segment CB. Why? Reflexive. Property of congruence. And then our sixth step is going to be, okay, so that would be side angle side. We know a side and an angle in between it and a side match with both triangles. So triangle ACB has to be congruent to triangle DBC. Why? Side angle side congruence. And you can write postulate or theorem as you remember them. You don't have to, okay? You can technically write side angle side and then congruence. And then we've got it. The next one, we're trying to show that these two triangles are congruent. Which ones? This one here with this one right here. Okay, we're trying to show that those two triangles are congruent to each other. Okay, that's what they ask us with the proof. So again, we're going to start our proof with what we know. Okay, we are given that EF is congruent to GH. And that's given. And let's mark it on our diagram. EF matches GH. Okay, so we've got a side. Okay, the next thing we know is that EH has to be congruent to GF. That would be an F. Let's learn our letters. Here we go. Ha. Step 2, also by given. Where is that on our picture? Let's look at it. So EH, okay, I'm going to mark that with a highlighter. So EH right there is congruent to GF right there. Okay, because it's given. So we know two sides. We know this side matches the other one. We know this one matches the other one. So we know two sides. Do we know any angles? Well, no. Do we know anything else? Well, yeah, the bottom. Okay, do you see that the bottom is part of both triangles? Okay, the bottom is the third side of both triangles, and it's the same measure. So we're going to say 3 FH is congruent to itself. Obviously, right? Why? Reflexive, property of congruence. And as a result, we know that the triangles are congruent. EFH is congruent to triangle GHF. Why? because we know three sides of the first triangle match three sides of the next triangle. So by side, 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 congruence. Okay, so it's kind of cute to see, hey, if we know three sides of one triangle match the three side corresponding sides of another triangle, then for sure the triangles must be congruent. Their angles will flow, they will match, they're going to be great. It's much shorter than doing all three sides and all three angles like we did yesterday. Okay, here's another one. All right, we're trying to show that those two triangles are congruent. So step one is B is the midpoint of DC. Why it's given. Okay, so B is the middle point of DC. So why did they tell us that? Well, if it's a midpoint, well, we know it's halfway, right? And we also know that means that these two have to be congruent. So we have to call that out and say, hey, guess what? That means that DB has to be congruent to BC. Why? The midpoint there. Okay, so we have one side matching another side in the triangles. Okay, so that's one side that we dealt with. Step three is going to be, all right, AB is perpendicular to DC. Okay, and that's given. Now, this is a little bit weird how we say it, so we're going to walk through it together. Okay, um, and then we can say step four. That means if it's going to be perpendicular, that means these are right angles. So we're going to call that out. Okay. Angle ABD and angle ABC are right angles. Why? Definition of perpendicular lines. Okay, so why are they right? Because you said they're perpendicular, that means they're right angles. And then we can call out to say, well, that means if they're right angles, that angle ABD is congruent to angle ABC. Why? Because of the right angle theorem. What's the right angle theorem talk about? All right angles are congruent to each other. Okay, so it's a little bit of a weird situation. We'll practice it. Write that down real cute so you can hold on to it. So if you need to use it again, you can. Okay, step six. Okay, I know one side matches another one. I know an angle matches another one. And then do you see the reflexive side in the middle? Okay, that AB is congruent to itself. It's also part of both triangles. So when we know a side, then an angle, and then a side, the angles in between the two sides we know. So AB is congruent to AB for a change, reflexive, property of congruence. And then step seven is those triangles have to be congruent. Triangle ABD. That's a nice voice. It's early in the morning. Triangle ABC. Notice I forgot a little triangle there. Okay. Why is it true? Because of side angle side congruence. I know two sides and the included angle in between them. Okay. Um, a lot of kids get confused. Like, I saw a right triangle. Do we have to use hypotenuse leg? Like, no, I don't know the hypotenuses match. I know that one of the legs matches. So whenever you look at a triangle, just because it's a right triangle, you can use the proof that applies to that one. Okay. If you're going to use hypotenuse leg, you have to have a right triangle, but it just because you have a right triangle doesn't mean you're going to use hypotenuse leg. So some kids get confused on that. Okay. Moving smoothly along. This one gets a little spicy, just heads up. Okay. What we're trying to prove is that this triangle here is congruent to the one at the bottom. Okay. And obviously they are. We're just trying to show it step by step. And the thing is, there's a lot of overlaps between angles and things. And so it's a little bit, special. So here we go. We know that 1 and 4 are congruent, and same with 2 and 3. Okay, so angle 1 is congruent to angle 4, and then also angle 2 is congruent to angle 3. Okay, so if I was going to do this proof, there's actually a couple ways I do it. They're leading us through one way, so we'll follow that. But there's a lot of things that you can, actually, I can see at least two directions you could do with this proof. And so that's kind of what proofs are. Sometimes there are alternate ways to do it. Because it's already frameworked here, we'll follow what they say. So obviously the reason why these two are congruent is because it's given. And then if you look at this, what happened from here to here? 1 and 4 are congruent. That means the measures of 1 and equal the measure of angle 4. That's the definition of congruent angles. Okay, remember if they're congruent, they'll be equal. If they're equal, their measure will be congruent. Actually, that doesn't make sense. If their measures are equal, then they will be congruent as well. Those are both directions to call them definition of congruent angles. The reason why they go to equality is because if you do that, you can add up their measures. You can say, um, and this is a little weird, I'll walk you through it. Notice they're going to do it like elimination. Remember, like in elimination, you take 2x plus 3y equals 8, and you add up two equations. And you add up vertically elimination. Well, what we're going to add up is the left side of this equation and put the answer here. Okay, and then we're going to add up the right side of the equation and put it here. Okay, and so because we're adding two equations together, this is addition property of equality. Okay, so we're adding two equations together, just like you do in elimination. And so, and then after that, we're going to look at our diagram and say, in our diagram, look at angle 1 and 2. If you add those up, um, and we're going to be a little bit weird, we're going to define angle N to be that top corner there. And we're going to say the measure is the measure of angle N really, should it be defined just by that? No, I just don't want to use two letters. So we're going to call this top corner the measure of angle N. Okay, so not the best, but for simplicity, because we're doing a lot today, we're going to call that top corner angle N. The more proper value would be to call it MNO. Okay, so this should be called MNO, but we're going to call it measure of angle N just for speed right this second. And then also, if you add up the measure of angle 3 plus the measure of angle 4, that would technically make this whole bottom angle. Okay, and so the measure of angle O. Technically, you should call it NOP, NOP, but for brevity, we're going to call it angle O. Okay, so just between us, we're going to kind of put that down there. Now, because these two right here are equal, okay, then we know that the measure of angle N equals the measure of angle O. Why? The transitive property. Okay, so since we're putting these two equations together, with angle 3, we're swapping out the whole side. It's the transitive property of equality. And then we can also say that angle O, angle N is congruent to angle O. So we finally have an angle. Okay, we got to an angle. So what have we shown that's congruent? Okay, I'm going to go back to our diagram. We've added those together because their parts are congruent. So therefore, in the top triangle, we know this angle up here is congruent to the angle at the bottom. Okay, if you look at this bottom triangle, this angle down here. Okay, so we've got an angle that matches the other angle. And then we also know from the given that NM and OP are congruent. So they tell us this matches this right there. So we've got a side. Okay, and then the last thing, okay, that's just given. The last thing we're going to do is we're going to say, well, do you see there's a reflexive side? Okay, over along the left. This left side over here is going to be part of the top triangle and the bottom triangle. So NO is congruent to itself. You don't have to flip the order. Somebody was just trying to be cute. Okay, and so in the top triangle, we know two sides and the angle in between it matches the two sides and the angle in between it in the bottom triangle. So side angle side congruence is going to be what we use. So there we go. We're going to look at this one here. If you guys don't get to it in the video, that's completely fine. This one here is kind of interesting how they do it. They say that, oh, I have this as optional. Okay, so you can stop the video if you want to. Um, they say that ACD and BCD are supplementary. Okay, and that's given. ACD and BCD. Oh, ADC. I'm not reading it correctly. ADC is supplementary with BCD. Okay, so that means that they add up to be 180 degrees. Okay. And so that means that these two angles are same side interior by definition. Okay. And then that means that if these are supplementary and they're same side interior, those two have to be parallel by the converse of same side interior. Okay. So we just kind of showed that these two lines are parallel. Okay. Okay, by the converse. So this tells us that those are parallel. If you draw, okay, I'm not going to ask you to draw stuff, but if you draw an auxiliary line here, okay, by the line postulate, what's that? 2 points determine a line. You can draw a line to connect any 2 points, okay? So it's a line postulate, okay? And ADB and CBD are alternate interior angles by definition of alternate interior. And because those lines are parallel, okay, then we know that those have to be congruent. So ADB has to be congruent to angle CBD by the alternate interior angle theorem. So we're going to have an angle. Finally, we have something that's congruent. Let's find it, okay? So where is that little angle? ADB right here is congruent to CBD. Okay, so we get an angle between the two triangles that we're trying to show are congruent to each other. Okay, what are we trying to show? We're trying to show that the two triangles that are formed because of our auxiliary line are going to be congruent. So this one here is congruent to the one below it. That's what we're trying to show. So we've got an angle in both of them that matches. We also are given that AD is congruent to CB. Okay, so AD is congruent to CB. So we've got a side. So we've got an angle and a side now. Cool. And then, oh, last thing we've got is that the new segment, DB, is congruent to itself. Okay, why? Reflexive property. So this side right here in the middle is congruent to itself. So you've got side angle side. Oh, that's my alarm. Okay, so we've got side angle side. Okay, below here, what we would do is we could say, could we use our compass and match each side and draw a congruent shape? Okay, if all three sides are congruent, then these two will be congruent to each other. Okay, could we copy this and do that? The other thing is, can you construct it using side angle side? So pick a side and match it, pick an angle, use a compass and a protractor to match it, and then pick a side and match it here. So can you match just those features and you will have that. So that would be just more of an exploratory situation where you could use a compass and a protractor to help us match those lengths and sides. So we are not going to get to that, but it's kind of interesting to see. All right. Thank you so much. I hope you guys have a great day.